Pause the video now and read the problem statement. Size of the problem is a plus b. Let's now look at the base cases. The instance of the problem with the smallest size occurs when a equals b equals 0. The second base case is when a equals 0, the result is b. The third base case is when b equals 0, the result is a. The second and third base cases makes the first base case redundant. The second and third base cases guarantees that a and b will be positive for recursive cases. Let's now look at problem decomposition. Size of the problem is a plus b. We can reduce the size of the problem by a unit. We can subtract a unit from either a or b. Let's look at the recursion diagram. The inputs are a and b. The result is a plus b. Going from input to the result requires a recursive function f.
F is in fuck, baby.
We can reduce the original problem to a smaller subproblem by subtracting 1 from a. This subproblem is also solved using the same recursive function f. The solution to the smaller subproblem is a minus 1 plus b. We need to extend the solution to the subproblem to find the solution to the original problem. In this case, we can find the solution to the original problem by adding 1 to the solution of the subproblem. The recursive case can be expressed by a function f of a and b equals f of a minus 1 comma b plus 1. This is the function to implement. The mathematical representation that includes the base cases and recursive cases is shown as f of a comma b equals b if a equals 0, equals a if b equals 0, f of a minus 1 comma b plus 1 if a is greater than 0 and b is greater than 0. Here is the code for the recursive solution. These two base cases correspond to the mathematical function cases for a and b. The recursive case corresponds to this case in the mathematical representation. We can choose b to reduce the problem size. This is our option number 2. We can reduce the size of the problem by subtracting a unit from b instead of a. The recurrence relation will be f of a comma b equals f of a comma b minus 1 plus 1 in this case. What will be the speed? It will be slow if b is large, because there will be more subtract operations needed to reach the base case. Let's look at an efficient way to solve this problem. We can choose smallest input parameter to reduce. If a is 10,000 and b is 2, the number of calls required to reach the base case is 2. If we choose B, when it is large, it will take 10,000 calls to reach the base case. Let's take a look at the decomposition approach number 1. We decrement the smallest input parameter. So the size of the subproblem is a minimum of A, B minus 1. Let's look at the recursive rule. If A is less than B, f of A equals f of A minus 1, B plus 1. Otherwise, f of AB equals f of A, B minus 1 plus 1. We are now ready to look at the mathematical function. F of AB equals A if B equals 0. It is B if A is 0. It is A minus 1, B plus 1 if A is less than B and A is unequal to 0 and B is unequal to 0. And it's equal to f of A, B minus 1 plus 1 if B is less than or equal to A and A is unequal to 0 and B is unequal to 0. We have two base cases and two recursive cases. Decomposition approach number 2. We decrement both parameters. This reduces the size of the problem. Let's now look at the recursion diagram. The inputs and the results are the same as before. We reduce the problem by subtracting one unit from A and B. The solution of the subproblem is A minus 1 plus B minus 1. In the combine step, we need to add 1 twice to get the result for the problem. The recursive rule can be expressed as for A is greater than 0 and B greater than 0. Let's now look at the code. We have two base cases that is the same as before. We only have one recursive case. It is the same as the recursive rule definition.
That's how we talk,